Hello, everyone. Let's get started here. And the last time we have been talking about data storage. Last time we have mostly focused on the hardware on which your data is stored. We have quickly seen the memory hierarchy, and we have discussed about a couple of different common data storage devices and their pros and cons and use cases. I have ended with this slide over here where I summarize certain common properties of those data storage devices and summarize points that will become important when we discuss about the design of database management systems, because a lot of that design is motivated by properties of the data storage hardware. Now, this time, I want to discuss a little bit more about not where the data is stored, but how the data is stored. We're going to discuss about different data storage formats. Now, so far, when we have been learning SQL, then you have thought about your data in the form of tables with different columns and rows stored in those tables. Of course, internally, we use a more low-level format. We have to somehow map this high-level perspective on the data to the bits and bytes that are actually stored. So in the following, we're going to discuss about this connection, about how we can map those this logical perspective to the physical storage reality. All right. So generally, for a given table, there's two things that we want to store. So first of all, we have the structure of the table, the schema, meaning like the column types and the constraints on the table. Now, this kind of information is stored in something called the database catalog. So that is a central repository of the database where it maintains certain metadata about all the data that is stored. The actual content of a table is stored as a collection of pages. And one of those pages typically fits a few kilobytes of data. So one page essentially corresponds to a chunk of data stored at one specific location on your storage device. And the size of those pages is chosen in order to maximize retrieval efficiency from the corresponding storage device. We have, for instance, seen for hard disks, there's a certain overhead in repositioning your read and write head. So once you have repositioned that, you don't want to read only a single bit or byte, but you want to read a little bit more data in order to make it worth it. And so those pages, they have a granularity that makes it somewhat efficient to retrieve and store data at those quantities, right? So one of those pages is typically not large enough to fit all the data from a relation, but it is typically large enough in order to store multiple rows from one relation. So that means that in order to store one table, we have multiple pages where each page stores multiple rows. And we have to somehow keep track. So this is an illustration of what we have just discussed. So the metadata about the table schema, which I associate with the table columns, that is stored in a database catalog. And then the content is stored as a collection of pages. All right. So we have multiple pages that store rows from the same table. So we have to somehow keep track which pages store information for a given table. So all those pages together, which contain data from the same table, they are called a file. And we have to keep track of which pages belong to a certain file. There's multiple ways of doing that. Now, one first possibility is that we store those pages that belong to the same table as a linked list, meaning that one page essentially contains pointers pointing to the next and to the previous page. And so if I want to retrieve the data within a table, I just follow those pointers and read all the associated pages. Now, that's a first possibility. A second possibility is to rather store a directory, which essentially are pages again that store references to those data pages. So in the following, I'm gonna illustrate those two possibilities. So the first possibility was that we store a linked list of pages. And this is how that would look like. So we have a so-called header page, which essentially that's the starting page if I want to retrieve data from the table. And then in order to make things more efficient, I can actually maintain two separate lists where I, in the first one, store pages that are full, meaning I cannot insert any more data. And in the second sublist of pages, I store pages that are at least partially empty. So this is helpful because if I want to insert new data into my table, then I can primarily look at the pages where I have some free space. And if I find one page with enough free space, then I can insert my new data there. Otherwise, if none of the existing pages has enough free space, then I want to create a new page in order to store the newly inserted data, right? So you can divide it into those two sublists, but in principle, it's a linked list, and the position of this header page needs to be stored somewhere at a fixed location. So that is typically also stored in the database catalog. The other possibility is that you have this so-called directory. So we have those directory pages on the left-hand side of the slide. And each of those directory pages contains pointers to the actual data pages. And the directory itself can again be stored as a linked list of pages. And again, we have this header page whose address you find in the database catalog. And those directory pages would also store some metadata indicating, for instance, how much free space is left on certain pages. So here, if I want to insert something, then I can mostly go through the directory pages in order to look for suitable data pages on which I have enough free space available. So since those directory pages are relatively compact and they can store pointers to many data pages together with associated metadata, it can often be more efficient to find, for instance, a matching page with enough free space using one of those directories. All right, and here there are some great questions in the chat. So for this format, you would typically only store the header page or the address of the header page in your catalog. And then in order to get to the other directory pages, you can use those links that are stored on the directory pages itself. All right. Okay, and here there's another great question. Why would we ever have more than one page with a free space? And the tricky point here is that the entries that I might want to insert could have different sizes. So at some point, you might want to insert an entry which requires more free space than the current pages offer. So maybe there's just there's a little bit of free space on each page, but not enough in order to fit the entry that you want to insert. So in that case, you would leave the free space on the current pages and rather create a new page which is completely empty and therefore allows you to insert the new entry. So that is one of the things that makes it complicated, that the entries that you want to insert might have different sizes. And the difference between those pages and the pages in the linked list before, there's no big difference. The only difference is that in the previous version, the data pages also store pointers to the next and previous data pages. Here, the data pages themselves, they don't need to store any pointers because their addresses are all stored in the directory. So that is a small difference, but otherwise it is the same. All right. So now those are possibilities how we can bind together different pages that store data from the same table. Now we have said that one of those pages stores data about multiple rows in a table. So we somehow need to partition the entire page into different sections that store different rows. And those page sections that store specific rows, they are called slots. So we have to think about how we can divide the space on a page into different slots for storing table rows, also called records in this context. So if you have partitioned the page into those different slots for specific rows, then in order to refer to one specific row, we essentially just need the page ID and the slot ID on that page. And both together, we will call that a record ID in the following. And that is indeed the way in which database management systems typically refer to specific records, meaning specific rows in your table, to the, like how they find them, for instance, on hard disk. There's multiple ways to divide pages into slots, and which one we choose depends a lot on whether my entries have a fixed length or whether they have a variable length. Now, for data types such as integers, for instance, Postgres dedicates a fixed number of bytes for storing each integer, 4 bytes, right? So if I have a table where all the columns are integers, then I can tell you a priori how much space I will need for each row in that table. If the table has 5 columns, 5 integer columns, then each row will need 20 bytes of storage, right? Now, the problem is that there's also data types such as text. And the space required by a text is not a priori fixed. It depends on the length of the text that you are entering. So if your table contains at least one column of type text or another data type whose size is not fixed a priori, that means that the space required to store different rows in your table might actually vary across different rows. And that makes it a little bit more complicated to divide those pages into slots. Now, we're gonna start with the easy case, which means that we need the same amount of storage in order to store each row in the table. So we can tell you a priori how many bytes we need per row. Now, in this case, we can essentially just uniformly partition the space on that page into slots that are just large enough in order to store one of those rows in your relation. So if you are considering different relations, different tables in your database, then the size of those slots might vary. But as long as we fix the relation, the number of bytes per slot are fixed and can be stored in the database catalog. So that makes a couple of things easier. The only thing that we still need to keep track of is that if I have multiple slots on a page, not all of them might be in use. So we still have to keep track which of those slots on my page are actually occupied by real records. And there's multiple ways of doing that as well. There's the packed way and the unpacked way, and we're going to discuss both of them in the following. Now, the packed representation essentially means that I'm using only consecutive slots on my page. So that means there will not be any holes, no gaps between used slots. All of those used slots are packed closely together. That's where the name comes from. If I do this, then the only thing I need to keep track of, it is the number of slots that are currently in use. If I know that I'm currently using 3 slots, it is immediately clear which ones it is. It is the first 3 slots because I'm using the packed representation. The unpacked representation is more flexible because it allows gaps between those different used slots. So if I allow this, then I need something like a little bitmap that I also store on the page, which tells me which of the slots are currently in use. In that case, I have a 1 at the corresponding bitmap position. Otherwise, I have a 0 at the corresponding bitmap position. Now, this is the representation of the packed version. Here I'm using the first 3 slots, and towards the end, I have the number 3, indicating how many slots I'm using. Now, this keeps things pretty simple. As long as I'm inserting data, it works actually pretty well. But perhaps think about it a minute. What happens if I'm deleting records? Can anyone write in the chat some propositions for why deleting records might be problematic with the packed representation? Mm-hmm. Mm-hmm. Yes, exactly. So many of you are pointing out that deleting one of those slots creates a hole, or called bubbles, or it leaves some kind of gap between the used records. And once I do this, in order to maintain the packed representation, I have to start shifting around records on my page. If there's a hole somewhere, I have to shift another record into this hole in order to stay with the packed representation. All right. And if I do this, okay, the first problem is that creates a little bit of overhead because I have to move, I have to copy other records around on my page. Can anyone think of a different problem if you think outside of the current page? If you think about the way in which we refer to specific records. And in the meantime, there's some remark about like how much overhead it would create in order to fill that that gap which opens up. As long as I delete one single record, I could also like move the last current record. I could copy that one or cut and paste that one from the last position into the hole. Then I would have a packed representation again. Okay, very good. Very good. Okay, and here I see what I was looking for. Very good. So we have said that we refer to records, to table rows, by the combination of the page ID and the slot ID. Now, if I move around the records on a page in order to fill gaps, it doesn't change the page ID, but it does change the slot ID. And so if I have external references, then I would need to update them in order to get back to the packed representation. So it would make things difficult. So an alternative way of doing this is the unpacked representation that you see here, and very good answers to the questions, by the way. So the unpacked representation allows gaps between different records, as you see here, and then you need a bitmap in order to keep track of which of those slots are currently in use and which ones are available. So here in the bottom row, you see the bitmap together with the flags indicating whether the slot is already in use or not. All right, now that was the little bit easier case where we have a fixed number of bytes per slot. Now, if I have text columns, for instance, then the number of bytes I need per entry will vary across different records, across different rows. So we are in the variable length case. Now, in order to do this, I need a way of keeping track where on my page specific records start and end. So typically you would store the starting position together with the length of the corresponding record. And we store the information again in a directory. But here we are talking about the directory that is stored on each page and keeps track of where specific record on that page are located. Right? Now, that creates a couple of opportunities for space optimizations again. So we have seen that in case of the packed representation, for instance, deleting slots can become problematic. If I start moving, like copying around records on my page, then that might destroy external references. Now, if I use those on-page directories here, that is not a problem anymore, because I can freely move around records on my page. The only thing that I need to update is this directory, which is directly stored on the page and which maps slot IDs to the corresponding positions. So since I have this additional layer of indirection in the form of the on-page directory, moving records around on my page doesn't destroy the external references anymore. Right? And I can exploit that in order to regularly compact my used space on a page by filling holes that have been left by deletions, for instance, and thereby I'm maximizing the consecutive free space that I have on my page. We have to decompose things even further, because one row, one record, typically stores data from multiple fields, from multiple columns. And that is why we need to think about how we can divide the space of a slot into space associated with different fields within that slot. And again, we're facing those challenges if my fields have variable lengths as opposed to a fixed length. For fixed length fields, for instance, if all of your fields are integers because all the columns in your table are integer columns, then we can just store the fixed length per column in our database catalog, and we don't need to store any additional metadata on the page itself in order to divide the slot into fields. Variable length entries make things a little bit more complicated again. And here we have two possibilities. The first one would be to use some kind of specialized delimiter symbol in order to separate the data from different fields. So that is one possibility. Another possibility is to use, again, the directories. Here, essentially directories at the beginning of each record, which tells you which part of the slot space is reserved for storing data in specific fields. So this is how we decompose everything down from pages to slots and to fields. Here, that is the summary of what we have been doing. One topic that keeps coming up, that is the topic of fixed length versus variable length content. Fixed length content is often easier to handle. If we have variable length content, then we need some kind of directory, whether that is a directory of pages, a directory of slots, or a directory of fields. So here we have reused the certain common ideas at multiple granularities. All right. And one question that is here currently, in the unpacked representation, do we still use slot IDs? Yes, we always use slot IDs. So in the unpacked representation, so that doesn't change anything. You still have slot IDs for the different slots, just that now you might have empty slots between consecutive used slots. So the slot is essentially the space reserved on the page for storing one specific record. And that space can either be used, occupied by a record currently, or not. So just because one of the slots is empty doesn't mean that it loses its ID. Okay? All right. Now, one last remark on how we store data. What we have been discussing so far essentially assumes that data which belongs to the same row is stored close together on a page. And that is the traditional way of storing data, which is, for instance, used by Postgres. Since it stores data from the same row close together, it's also called a row store architecture. Nowadays, there is another breed of database systems which stores data differently and rather tries to store data from the same column close together. That can be a performance advantage in cases where your queries tend to access only a few out of many columns of your tables. If you have this, then with the row store format, you would load entire data pages. Like one of those pages is the unit at which we retrieve data, for instance, from the hard disk. And if you load one of those pages with the row-wise format, it would contain data about all the different columns for specific rows. And if I'm not interested in many columns, it means I'm loading a lot of data that I actually cannot use. And in those cases, a column store architecture might be more efficient. But that is a topic that we will discuss in more detail later, where we will also see specific systems that use this newer column store format. All right. Now let me quickly change the slide deck here. We're gonna continue with the topic of how we store data, but we're gonna see more sophisticated ways of storing the data that make retrieval more efficient. And those are the new slides. I believe that you should all be able to see the tree indexes slide deck now. All right. Okay. So in the following, we're gonna discuss more about how we can store our data in order to make access as efficient as possible. So within this big architecture of database management systems that I have initially introduced, this concerns the data itself, the way in which we store it, as well as this component that I have named data access within the storage manager, which contains the algorithms that exploit data structures for efficient access and that handle them. The relevant chapter in the Ramakrishnan and Gerke book, that is chapter 9 for what we discuss in this slide deck. And the problem that we will be looking at in the following lectures, that is the problem of quickly finding specific entries in your data set. Now, to make things a little bit more concrete, think, for instance, of the enrollment table that we have seen in our example database. The enrollment table contains information about the students and the courses that they're taking. So it essentially contains pairs of the student ID and the course ID with the semantics that the corresponding student is taking the corresponding course. And now let's imagine that we are searching for the enrollments for one specific student, for instance. Maybe we want to find the enrollment information for the student with SID 5. Now, if I store data using the format that I have introduced directly before, then I could, for instance, store the data from the enrollment relation as a collection of data pages, and might either have them as a linked list or as a directory. So in order to find the enrollment information for the same student, I would have to go through all of those pages and to look at all records on each of those pages in order to check whether the student ID equals to 5. And as you can imagine, if I have a lot of students, then that is actually quite inefficient because I need to look at all data, but I'm only looking for a small number of entries typically. A better version is already if I just sort the data by the student ID. If I have sorted my data by the student ID, then I can apply something like binary search, for instance, in order to narrow it down quite quickly to those entries that I'm interested in. So that is already significantly better. But the problem is this. For one data set, I have to choose one specific way of ordering it. So here, for instance, if I choose to sort the enrollment relation by the student ID, then it will make it more efficient to find information about specific students. But if I'm now searching for information about specific courses, for instance, even worse, then the student sort order doesn't help me at all. And I have to choose one single sort order. So in order to make multiple ways of accessing your data more efficient, we can use something called an index, which is essentially an auxiliary data structure used for finding data faster. And indexes are really exactly the same principle as indexes for books. I mean, here, for instance, I have this New York tour guide, and in the end, it has an index which contains the names of different attractions sorted in alphabetical order. And for each of those attractions, it has a reference to the pages on which I find the associated data. And indexes and database management systems, they do exactly the same thing. And the nice thing about them is that I can have multiple indexes for the same table. So for the enrollment table, I could create one indexes for quick lookup of specific students and another index for quick lookup of specific courses, right? And that means I can make multiple ways of accessing data in the same table more efficient with that method. Now, in more detail, the index stores references to data records. And as we have just seen, those references have the form of a page ID and a slot ID. Now, indexes, they always refer to one specific table, at least the indexes that we see here in the lecture. And indexes are always specialized for one search key. So the search key, that is essentially a subset of table columns. And then the index helps you to quickly retrieve entries that have specific values in those search key columns. You want to search according to different columns, then you need a new index, basically, right? Okay. So let's start with a simple indexing example. So let's say that I want to retrieve enrollment information for specific students, then I can create one of those index structures in order to make access by student name more efficient. Now, the data of the index itself, because it's also data, so we again store it as a collection of pages. So the index is also stored as a file. And here in this simple example, you see that I have multiple pages that belong to the index. And each of those pages has on the left-hand side the values from the search key, which in this case is the student name column. And on the right-hand side, you find the record IDs, meaning the page ID followed by the slot ID. In order to keep the example simple, I have made those pages fairly small. So we have at most 3 entries per page. In reality, of course, you would have typically hundreds of entries per page. So here you have the index page ID for the pages that store the index data. And as I have already discussed, on the left column, you have the index search key. On the right column, you have the associated record ID. And now if I search, for instance, for a student named Alan, then I can use something like a binary search in the index. I can first look at page number 14 and see whether the entries on that page come before or after the entry that I'm looking for. So here those student names, they are ordered in alphabetical order. So Alan comes before Kyle. So I have to go to the left side of that page number P14. All right, so that would be P12. And now I compare against, and Alan becomes even before Felix. So I have to check out this one, and Alan also comes before Dora. So now I have found the last page. And here I had to access 4 pages in order to retrieve the data I'm looking for. And we have already very quickly discussed this, but let me remind you that in the context of database management systems, often the cost for accessing data actually dominates entire processing cost. And that is why those index structures that we will see, they're optimized for minimizing the number of pages that I need to load from hard disk in order to find the data that I'm looking for. So according to that cost metric here, we would have loaded 4 pages. So that means 4 cost units for the access. Then finally, since the index only contains a reference to the actual data I'm looking for, I would still need to count 1 more page access in order to load the data that is referred to for Alan, which I find at page number 25 in slot number 3. Now that is one first simple indexing structure, but in the following, we're going to improve on it. Now, the first thing that we want to improve is this. Right now, I have a flat index structure which sorts by the student name, and that means I can use binary search. So with binary search, whenever I load a page from hard disk, it means that I'm essentially narrowing down the search space by factor 2. The index structures that are actually used in database management systems, they try to be more efficient per page access. So they try to narrow down the search space by a much higher factor than 2 for each page load operation. And I can do this, for instance, using so-called index trees, tree indexes. They will be the focus of this and still the following lecture. But already as a little outlook, there's essentially 2 big branches of indexing types. One is organized as search trees. One is organized as hash tables, basically. And we're going to first discuss the tree indexes. Later, we're going to discuss about the hash indexes. This is how I can use one of those tree indexes for this example here. As you see, now we have more pages in the index. The index data that we have seen before, it's still there. It's now the lower level of the tree. And we have multiple levels above that. Now, if you compare the content in pages on the upper half of the screen to the ones on the lower half of the screen, basically below that green dashed line, then you see some slight differences. So the entries on the lower part of the screen, those are the so-called data entries, because here each entry on a page references specific data. So in this case, there's a specific student names, and next to it is references to where you can find that data. If you look at the entries on the upper half of the screen, then they are organized a little bit differently. So those entries on the upper half of the screen, those are so-called index entries, and they don't point to actual data, but they point to other pages from the index itself, right? So here the semantics is this. On the columns on the left-hand side in those index entries, we essentially have references to a specific key ranges, search key ranges, and then on the right-hand side you have references to associated indexing pages. Now, in order to make things more concrete, let's have a look at a concrete example again. So we are searching for this student again. And in order to use one of those index trees, we always start at the root node, which is the node at the very top. So here I'm looking for student Alan. And student Alan would be ordered before Holly in alphabetical order. That is why I need to go to the corresponding page 2 of the index that is referred to. So now I'm looking at the page number 2, and again I'm comparing, I'm searching for Alan. So Alan comes also before Dora, so I want to look at the index page 10. And now I'm at the right page, and here I'm finding an entry for Alan. And because of that, I know that I find the corresponding enrollment information on page number 25 in slot number 3. And here I have some discussion about like pointers. I assume the question is whether those record IDs essentially correspond to pointers, and that is pretty much the case. So they give you one specific address where you can find data that you are looking for. All right, so here to make things a little bit more formal, a description of the content that we have in those different types of nodes. Now, in the inner nodes of the index, we have those index entries, and the content that they store, it's alternating between references to index pages and search keys. So we alternate between the two with the semantics that the references point to entries that are strictly ordered before the key that you find next, right? So here, for instance, a reference 1 would point to entries that come strictly before search key number 2, right? So if you're searching for something, then you just need to identify the corresponding key value range within one of those inner nodes in order to know which index node you need to look at next. The leaf nodes are structured a little bit differently. They have keys followed by references, so it doesn't start with a reference, it starts with a key. And for each of those keys, the corresponding reference contains a link to the data that is associated with this search key. So we can use those indexes, first of all, in order to answer queries with equality predicates. And we have already seen that, for instance, if I'm looking for a rows satisfying the condition student name equals Alan, then I can use the index that we have just seen in order to efficiently answer them. What I can also do is to use them for inequality predicates. For instance, if I have an index by the GPA column, then I could use one of those index in order to quite efficiently retrieve those entries with a GPA greater than 3. We're gonna see in more detail how retrieval works in those cases in the following. Now, in any case, this works if the predicate that you have in your query references the index search key. All right. So here, to make things a little bit more concrete, how can we use this index for equality predicates? This is the algorithm that you would use for that. So whenever I have an equality predicate in my query and I want to use the index in order to find corresponding entries, then first of all, I start at the root node of the index, which in those slides was on top. And until I reach one of the leaf nodes, I essentially, for each node, identify the right key value range that the entry I'm looking for must be contained in. Then I follow the corresponding reference to the next index node, and so on until I reach one of the leaf nodes. And at the leaf node, I see whether an entry exists for the corresponding key. And if I find such an entry, then I follow the record ID in order to retrieve the associated data. So of course, whenever you use one of those indexes, it is not guaranteed that you find any entry at all for the key that we are looking for. Perhaps we don't have any student named Alan registered, right? But at least the index directs you towards the leaf page on which the entry would be located if it exists. So after we have examined that leaf page in the index, we can be certain one way or another one whether the entry is in the index or not. All right. Now, there's a couple of optimizations of those index data structures that we will discuss in the following. Gonna quickly outline the first one, and then we will discuss more in the following. Now, often I might want to retrieve multiple entries from an index. For instance, if I have one of those inequality conditions, in that case, it can be good for performance if the leaf nodes of my index are also linked to each other. So if I want to retrieve information in neighboring leaf nodes, I don't need to go over the parent nodes anymore, but instead I can leverage those links in order to go from one leaf node to another one. And this is how that would essentially look like. So imagine, for instance, that we want to find all students whose name starts with a letter between D and K. Then I could use this index in order to find the first student whose name starts with a letter D, which is Dora over here. And using those links between the leaf pages, I can just start from the Dora page, which is page number 11, and then jump to page number 12, to page number 13, to page number 14, until I find entries which start with a letter after K. And so I can quite efficiently use the index in order to retrieve those students whose name starts with a letter between D and K. And what enables me to do that is linking the leaf pages in my index by essentially storing the pointer to the next and the pointer to the previous leaf page in each of those leaf pages. Okay. So that was one optimization. We will see more optimization and different indexing variants next time. The homework, by the way, will be out this afternoon. You will find it on CMS, and I had questions about putting it on different platforms. So I will also put it on Piazza. And you have 1 week for doing the homework. It focuses on SQL as promised. And yes. Right. Good. Then have a nice day, and see you on Wednesday.